Hi everyone, welcome to Fun Math in Daily Life. We are Youth STEM for Humanity Coalition, and this is our sixth webinar series that we present monthly about different topics and how they relate to daily life. Today, our presenters are me, Cecilia, Benjamin, Angelina, Derrick, Isabelle, Angela, and Edward. Here's a quick overview of what we're going to be covering today. First, I'll be presenting about graph theory in daily life. Angelina will be presenting a bit more about graph theory in daily life. Derrick will be presenting about math puzzles and games. Edward, Rubik's cubes. Isabel, also Rubik's cubes. Angela, financial math in daily life. Benjamin, cooking with math. And Cecilia, gardening with math. Okay, and then before we get started, let's go around and then do a self-intro, and we are the speakers. I'm Emily. I'm president of Youth STEM for Humanity Coalition, and I'm a freshman at Brown.
I'm Angelina Willis. I'm a board member of Youth STEM for Humanity Coalition, and I'm a sophomore at Northview High School.
Hello, I'm Derrick Kwan. I'm also a board member, and I'm a 10th grader at the California Academy of Mathematics and Sciences.
Hi everyone, my name is Edward, and I'm from South Point. I'm seventh grade.
Hi, I'm Isabel. I'm the Assistant Director at Physics for Humanity Circle at the Youth STEM for Humanity Coalition, and I'm a sophomore at Westlake High School.
Hi everyone, my name is Benjamin Yang, also called Junjie Yang, and I'm a 10th grader at Diamond Bar High School. And I'm currently serve as an assistant director for the Math for Humanity Circle.
Hi, my name is Angela, and I'm also a board member, and I'm currently a sophomore at Diamond Bar High School.
Hi, I'm Cecilia, and I'm the director for Biomed, and I'm a junior at high school.
And then if you're new to our entire webinar series, we are Youth STEM for Humanity Coalition, and we're a global student organization dedicated to bridging STEM and society, as well as cultivating creativity and compassion in our future leaders. We're just a group of passionate individuals dedicated to using our STEM skills for positive social and societal impact. We're all very enthusiastic about organizing events and driving meaningful change in our communities. If you're eager to make a difference in your local community, you can feel free to apply to join to be part of our student board and help drive those positive changes in our society. And here's our website. You can send us an email if you're interested in joining. First, let's talk about graph theory. Graph theory is the study of graphs, and maybe when you hear the word graphs, you might be thinking of like the Cartesian plane with like an x-axis and y-axis, and then you plot things like draw lines. In discrete math, the definition of graph is a bit different. So it's a mathematical representation of a set of objects where these objects are called vertices or nodes, and the lines connecting the vertices or the relationships between them are represented by edges. So here, this entire thing is called a graph. And then at each one of those dots that you can see, each one is called a node. A node represents basically an object. Between those objects, there are relationships connecting them, and then those relationships we call edges. And graph theory, this is kind of like an abstraction to make sense of the world around us and the relationships between different objects. So it's kind of converting abstract relationships into something that we can visualize on a paper. A fundamental story in graph theory is the seven bridges of Königsberg. So this is a famous problem in graph theory proposed and solved by Euler in 1736. This problem involves a Russian city called Königsberg with four pieces of land and seven bridges connecting them. Here you can see there are four pieces of land. There's this middle section, this section, and the rest of the section. And then in red are the seven bridges. The challenge is to basically walk around the city, crossing each bridge exactly once, and return to the starting point. And you're not allowed to go back to a previous bridge. Like for example, if I trace it in this direction, then I am stuck here. I can't go backwards to reach the remaining bridge. So that would not be a valid path. Like if I go this direction and then go here, then I would be missing out on this bridge. So basically your goal is to cross all seven bridges without going backwards, and you want to traverse all of them exactly once. This problem laid the foundation for graph theory and remains a classic example of how graph-based analysis can solve real-world connectivity problems. How Euler came up with kind of a proof to show that this isn't really possible is he represented the land areas as vertices, so each one of the huge chunks of land surrounding the river that flowed through the city, he represented using a vertex. So for example, this huge chunk of land is just represented as a dot. So we want to simplify as much as possible into a graph. This chunk of land is just a dot called a vertex. Same with this chunk of land, it's another vertex, this chunk and this chunk. So 4 vertices. And he showed that for a graph to have such a path as described earlier, certain conditions must be met. So the graph must be connected, and each vertex must have an even degree. And degree is basically the number of edges that you see extending out of each vertex. So for example, for vertex 5, you see that the degree is equal to 5 because there's 1, 2, 3, 4, and 5 edges extending out. However, in Königsberg, each piece of land had an odd number of bridges. So these numbers that we see here indicate the degree for each vertex, and all of them are odd. Euler proved that it was impossible to find such a path because of this odd or even rule, because all of those vertices need to have an even degree in order for this condition to be met. So that's a very classical problem that kind of started the field of graph theory. Another famous problem in graph theory is the 4-color theorem. It deals with the coloring of maps using 4 different colors in such a way that no 2 adjacent countries have the same color. It was first conjectured in the 1850s and it was finally proven in 1976 with the help of computers. It's not just countries, but like even if you take, a map of the US with the 50 states and then you want to color it in 4 different colors, this 4-color theorem basically gives you a solution to that. There's another problem, traveling salesman problem. This can also be modeled using graph theory. In this context, cities are represented as nodes or vertices in a graph, and the roads or paths connecting them are represented as edges. The distance between cities becomes the weight assigned to each edge, and the goal of this problem is to find the shortest possible tour that visits every city exactly once and then returns to the starting city. So it's a bit similar to the 7 bridges of Königsberg problem because your goal is to pass through each vertex once without traversing backwards. There is a weight assigned to each vertex based on the distance between that vertex and its adjacent vertices. And then some definitions that are essential to graph theory. First of all, a graph, which we define as G, consists of a non-empty vertex set, which we call V of G. And V of G includes all the vertices which we can assign this label, like we can call, for example, this vertex V1, V2, V3, V4, and V5, and is basically the number of vertices. So for example, here n would be equal to 5. So we're labeling all the vertices with this label, essentially. A graph can be partitioned into a vertex set and an edge set. An edge set is E of G. It includes the elements E1, E2, all the way to En. For example, here, this could be edge 1, this is E2, E3, E4. The number of vertices and edges can be denoted as using this absolute value sign, which just represents the cardinality of the set, which is basically the number of elements within the set. For example, if you have 5 vertices, the size of your set would be 5 because there is V1 all the way to V5, and then there's 5 elements within VG. So then the size of VG would be 5. Each edge has either 1 or 2 vertices associated with it. An edge connects its endpoints. A graph can exist in different forms. The 2 graphs in the figure are actually the same graph, but in different forms. Let's try to rearrange this graph into this graph. So if we just move this vertex to over here, if we move this one to here, so that those 2 vertices are parallel, then we notice that they're exactly the same graph. No matter how you move the vertices or edges, as long as they retain the same connectivity, you'll end up with the same graph, despite the transformations. A walk is a sequence of vertices with each vertex adjacent to the next. A trail is an open walk in which no edge is repeated, but vertices can be repeated. A path is a trail in which neither vertices nor edges are repeated. This is a walk. So it's just a sequence of vertices. For example, if you go 1, 2, 3, 4, 5, 6, notice how you're repeating this edge. It doesn't really have any conditions that have to be met. A trail is an open walk in which no edge is repeated. So if you go 1, 2, 3, 4, 5, 6, then notice how you're not repeating any edges, but you are repeating this vertex because 2 and 5 correspond to the same vertex. And then a path is a trail in which neither vertices nor edges are repeated. So if you just go 1, 2, 3, 4, 5, you're not repeating any vertices nor edges. And then a cycle is a closed walk where neither edges nor vertices are repeated, except that the starting vertex and ending vertex are the same in a cycle. So basically, your start point and end point are the same vertex. Yeah, if you go from D, B, A, C back to D, that's a cycle. Next is a tree. A tree is a connected graph with no cycles, so you can't really form any loop in your graph. A graph is a connected graph if there is a path between every given pair of vertices. A graph is disconnected if it is not connected. This is a connected graph because there is a path that helps you traverse between every given pair of vertices. Like between this vertex and this vertex, there is a path. There's another path that you can go through to get there. This graph is a disconnected graph because there's no way to go from this vertex to this vertex. And the purpose of all this is to help model, analyze, and interpret many complex situations in real life. For example, biological systems and relationships, which Angelina will be talking about in the next few slides. Those can all be modeled using graph theory because essentially graph theory is just an abstraction that allows us to convert something in real life that might be intangible into something that we can see using nodes or vertices and edges. Next, Angelina will talk more about how graph theory is applied in daily life and scientific research.
Hello. Next, we'll be going more into graph theory. So we just learned that graph theory is a useful tool to interpret complex biological systems and relationships. It also reveals important patterns in biological data. So an example is the use of graph theory in ecological food webs. Food webs are graphical representations of the complex feeding relationships and interactions among different species in an ecosystem. So this figure shows species represented as vertices in the graph and predator-prey relationships represented as edges. So the arrows are the transfer of energy and matter between the organisms. In 2008, a group of ecologists conducted research on the coupling between grazing and detritus food chains and the strength of trophic cascades across a gradient of nutrient enrichment. So as shown in this figure, they constructed a minimal food web model using graphs and grazing detrital food chains linked by nutrient cycling and generalist top predators. To be specific, in this graph, the top predator is the carnivore. It is consuming its prey, which is the herbivore and the detritivore. For example, the arrows are both pointing towards the top predator, meaning that they are transferring their energy and matter into the carnivore. And the carnivore is then transferring its energy outside of the food web because it is the predator. Now let's take a look at graph theory applied in protein analysis and scientific research. Protein-protein interaction, or PPI network, are mathematical representations of the physical context between proteins in a cell. The interactome refers to the entire set of PPIs occurring within a cell, organism, or specific biological context. Advancements in large-scale PPI screening techniques have led to a substantial increase in the amount of PPI data. So as shown in the next figure, proteins are represented by vertices in the graph, and the interactions between proteins are indicated by connecting edges between the vertices. So the graph shows the following protein-protein interactions. As you can see, protein A is interacting with protein B and protein C. Protein B is interacting with protein D, and protein C interacts with protein E, and protein D is interacting with protein E. Researchers could then visualize and analyze the PPI network using graph theory techniques and determine node or vertice degrees, network connectivity, network centrality, and community detection.
Hello. So yeah, we'll be going over some math puzzles and some games for you guys that you guys could do. And then, yeah, let's get started. So our first game is a game where we have four numbers from 1 to 9, and then you want to hit a target that is from 1 to 40, and you want to find as many answers as possible. You could use any operations, including factorials, triangular numbers, rectangular numbers, and logarithms and exponents. Right? So the most solutions will win, and we'll have 60 seconds to solve it. And then there'll be examples under it. Let me set a timer for 60 seconds, and then you could click the slide again, and then the image will show. So you'll use 1, 2, 5, and 9 to hit the target of 45, and we'll be giving you 60 seconds to solve, starting now. Okay, time's up. If you want to type in chat, like how many numbers you got, and then you want to explain your solution, that would be great. But if not, we can move on. This one's a little more simple. So basically, we'll have a 3 by 3 grid, and then it's like tic-tac-toe, where you could use the three numbers in a row or a column or a diagonal to hit the target. So you need to use at least two operations. You could use the same operation. You can't use the same operation, and you'll be able to get the solution that the target. Okay, so I'm gonna start the timer right now. The chosen answer is 5, and we'll be given a 3 by 3 grid, and these are some of the example answers. So after giving you guys 2 minutes, it was a little longer. You guys want to list out how many solutions you guys had? Keep in mind for this problem, there was 26 solutions for this grid. There was 26 solutions, and for the first row only, there was over 10 solutions. The example answers were like the most obvious ones, but then even with like the other rows, there were at least 5 answers with the other rows too. So for the next slide, I'll give you guys more time. A little secret with this one is that if you use 4 factorial, it'll be really, really easy to get 24. Like it's like a trick method to get 24. So the rule for this one is we'll be rolling 4 dice. So the numbers will be from 1 to 6 to make the result exactly 24. So our target's 24 this time, but you'll only get 4 numbers from 1 to 6. Okay, so after 2 minutes, how many answers were you guys able to get? 2 solutions? Okay. Anybody could beat 2 solutions? 2 solutions, another 2 solutions. Okay. 2. Everybody got around 2 solutions. The little trick to this type of problem is that if you figure out that 4 factorial is equal to 24, you try to get the other numbers to be equal to 0. And then you'll be able to find ways to get 24 for several different solutions. Yeah, so what's the point of all this and how does it relate to daily life, right? So this helps your problem solving skills as it helps you to think clearly and logically, just like when you're figuring out real life challenges. It also boosts problem solving abilities, right? It helps engage with numbers of challenges and builds logical thinking. And confidence in math is really, really important. In solving these game challenges, it can help reduce your math anxiety and also help build your confidence. And strategic thinking is something that's vital in your daily life, as players will help develop skills by solving for multiple solutions. And focus and patience, right? Many puzzles require close attention. Although 2 minutes wasn't a long time, if you were given more time, I'm sure you guys would be able to solve so many more solutions, get so many more solutions, right? And the most important thing is it makes learning fun. If you turn math into a game, it makes practicing it way more fun. So you have motivation for it in the future. So I'll be handing this off to Edward so he could talk more about Rubik's Cubes.
Hello everyone, my name is Edward. Today I want to share something really fun, the Rubik's Cube. I will show you how the Rubik's Cube is not just a toy. It also teaches us about numbers, patterns, and thinking skills. Let's start it. Please guess how many steps it will take me to solve this Rubik Cube. There are many kind of Rubik's Cube. The small 2x2, the regular 3x3, and the big 4x4 cube. Do you know how many ways we can mix them up? The 2x2 cube has about 3.6 million combinations. The 3x3 cube has more than 43 quintillion. And the 4x4 cube, it has a number with 45 zeros. Can you guess how many moves are needed to fix a mix-up Rubik's Cube? The answer is only 20 moves. That means even the most mixed-up cube can solve in 20 steps or less. If you use them the best way, in 2010, a group of scientists and Google used computers to test every possibility. It took them years to prove it. This number 20 is now called God's number because it's the smartest way to solve the cube. Solving the Rubik's Cube is not just fun. I also learned a lot from it. First, I learned to focus. I have to too careful and think step by step. And most of all, I started to enjoy math more because the Rubik's Cube is full of math thinking. Thank you for listening.
Okay, I will also be talking about the math behind Rubik's Cubes today. So I'll focus primarily on a 3x3x3 cube. So a 3x3x3 cube has 9 squares on each face and 6 different colors, which means there are 54 stickers in total. There are 8 corner pieces, 12 edge pieces, and 6 centers. Each time you twist a cube, it changes the cube's permutations. And as he already said, there are 43 quintillion possible permutations for this type of cube. To get 43 quintillion permutations, there are 8 total corners that can be arranged in 8 factorial ways, and they can each be oriented 3 different ways because there are 3 colors showing. And that means that there are 3 to the 8th possibilities for the permutations of the corner pieces. And then the 12 edge pieces can be arranged in 12 factorial over 2 ways and flipped 2 different ways because each edge piece has 2 colors, and then there are 2 to the 12th possibilities for the permutations of edge pieces. It's 12 factorial over 2 ways because of parity, which is a special case. So the formula to get the total amount of permutations is 8 factorial times 3 to the 8th times 12 factorial over 2 times 2 to the power of 12. Fun fact, if you turn the cube 1 time each second, it would take more than 1.4 trillion years to go through each combination. So as Edward mentioned, God's number is the minimum number of moves to solve any scrambled Rubik's Cube, and no matter what, it can always be solved in 20 moves or less. And this is proved using group theory, which is a branch of algebra that studies sets with operations. So for the cube, each move is an element of the group, and then a sequence of moves are the compositions of elements. And order matters in this case. So moving the cube right and then down is not the same as down and then right. And then the basic moves for a cube are up, down, right, left, front, and back. There are many algorithms that are used to solve Rubik's Cubes. For example, right down, right up, right down, left is a pretty commonly used one. And combining these moves can create new positions. And this is what people in speed solving competitions use because they memorize specific algorithms that help them solve the cube faster. However, some cubes are mathematically unsolvable. For example, if you peel off the stickers and then reassemble the cube, there's a 50% chance that you can't solve it. So speed cubers use commutators, which are math-based move sequences, to limit the amount of steps that they take to solve the cube. And the world record is 3.13 seconds. Yeah, and that's it.
Hi, my name is Angela, and today we will also be going over some basics in financial math and as well as some financial literacy. As we know, money is super important, but managing money isn't just about spending less. It's really about making smart choices. And so needs versus wants. So that's where needs are things you can't live without, like food, shelter, and basic clothing, while wants are the things that are too nice to have, but they're not necessary, like video games, fancy shoes, and as well as the latest iPhone. So, like when you budget your money, it's important to know the difference between the two. So, next is something called opportunity cost. So, this means that every dollar you spend on one thing is a dollar you can't use for something else. If you spend $20 on snacks, that's $20 you won't be able to save or use for something else. So, let's look at the budget equation. Income equals needs plus wants plus savings. This means that whatever money you have coming in should be divided wisely between what you need, what you want, and what you save. And so we can use optimization to figure out the best way how to spend our money. And that means we can use inequalities and constraints to find the smartest budget. So for example, let's say your total income was $200. We're trying to find the best value for N, which is needs, W, which is wants, and S, which is savings that fit into these rules. And so N has to be at least 51% of your income, and W can't be more than 31%. And so to maximize your savings S, we use the formula S equals I minus N minus W. And if we plug in some values like N equals 100 and W equals 60, then S equals 40. And so that's a good example of reducing your wants to save more. So now that we looked at smart spending, let's talk about savings. One of the most powerful tools in saving is compound interest. And so that's when you earn interest not only on your original money, but also on the interest you've already earned. So your money starts earning more money. And so the formula for compound interest is A equals P times 1 plus R over N to the power of NT, where A is the amount you'll have in the future, P is the starting amount or your principal, R is the annual interest rate as a decimal, and then N is how many times the interest is added per year. And then T is also the number of years you leave the money invested. The more often interest is added, the longer you wait, the more money you grow. And so there's also continuous compounding where interest is added nonstop instead of on a schedule. And so this uses the formula A equals per, also P times E to the power of RT. I'm using lumps. For regular compounding, we have this equation. And then for continuous compounding, we also have the other equation. So to compare different saving or investment options, we use the effective annual rate or the EAR, which is 1 plus R over N to the power of N minus 1. And so this tells you the real growth over a year, taking the compounding into account, and also helps you decide which investment option is better, even if they have different compounding frequencies. So now let's take a look at something that affects everyone who earns money, which is taxes. So first we have gross income, which is the total money you earn before taking out any expenses or taxes. So it's your raw earnings. And then we have the net income, which is what's left after all expenses and taxes are taken out. So your actual profit or what you actually take home. So, and we can model this simple formula by using net income equals G times 1 minus T, where G is your gross income and T is your tax rate. And so this gives a quick way to estimate how much money you'll actually get to keep. But taxes aren't just one simple rate. So we often deal with progressive tax systems where the rate increases as your income increases. And so this is where piecewise functions come into play. So in this piecewise functions, you can see that you pay 10% on the first $10,000 you earn, and then 15% in anything between $10,000 to $40,000. And then lastly, 25% on anything that's $40,000. And so this structure helps show how marginal tax rates work. So each portion of your income is taxed at a different rate. So earning more doesn't mean your whole income is taxed at a higher rate. It's just the part that goes over the threshold. So on the left, you can also see a real world example of how expenses are subtracted from revenue to calculate the net income for a business. So understanding how taxes work, especially using functions and equations, helps you figure out not how much you owe, but how much you actually get to keep. And so lastly, let's wrap it up with how businesses make smart decisions, specifically with cost structures and profit maximizations. So what are paying types? The first, which how much you produce, like rent or salaries, or variable costs, which change depending on how much you produce, like materials or utilities. So understanding these helps businesses decide how scalable they are or how easy they can grow without costs exploding. So now, to make the most profit, businesses need to figure out how much to produce or invest. And that's where calculus and vertex analysis come into play. So take a look at this profit equation where X is the amount of a resource being used, like hours worked or units produced. So to maximize the profit, we take the derivative to find the critical points, and we set that equal to 0, which gives us X equals 3. Or we can also use vertex analysis, which gives us the same answer, X also equals 3. That gives us the maximum. And we substitute X back into the equation, which gives us the -2 profit. So this actually shows a loss, not a profit. And that's also important because it tells us how that even the best use of resources doesn't always lead to a positive return. It helps us know when to change the business plan as it's needed.
Hello everyone. So my name is Benjamin and also called Junjie, and welcome to my presentation. My presentation is Cooking with Math, the calculus of chocolate chip cookies. Today I'm going to talk through the process of baking cookies step by step. And in each step, I'll show you how math quietly plays a role. So let's start in the kitchen. So we begin by gathering ingredients: flour, sugar, butter, eggs, baking soda, and the chocolate chips. So we mix everything together into a dough, knead it until it's smooth, and roll it out into a big flat circle. So now we can move on to step 1 of baking, shaping the cookies. Instead of using pre-made cookies cutter, we are going to design the cookie shapes ourselves by using the geometry. So let's start with the star. We begin with a circle. Imagine its radius is 1. Just keep things simple. So inside the circle, we draw a regular pentagon, a 5-sided figure with all sides and angle equal. Since a full circle is 360 degrees, each central angle between the vertex is 72 degrees. By connecting every other vertex of the pentagon, we get a 5-pointed star that both symmetrical and well balanced. This shape also has 5-fold rotational symmetry, so meaning it looks the same after every 72 degrees rotation. So next, let's look at hearts. So we use the same circular doll, but this time we place a square inside the circle. The square is rotated 45 degrees, so it fits like a diamond within the circle. Then we add 2 semicircles to the top corner of the square. Together, the square and the semicircles form a heart shape. So one that looks smooth, symmetric, and visually pleasing. And the most importantly, everything fits perfectly within the circle. Let's deal with the area. If we treat the circle's radius as 1, then the full area of the doll is pi. The star shape uses about 60% of that total area, and the heart uses about 84%. Here's a question: what shapes should the tray be? Let's say like we are designing our own tray using a strip of metal that exactly 40 centimeters in perimeter. We want to fold it into a rectangle and we want to maximize the area so we can fit as many cookies as possible. To solve this optimization problem, we begin by assuming that the total perimeter of the rectangular tray is 40 centimeters. So let's call the length of the tray X and the width Y, since the perimeter is the total length around the trays. So we know that 2 times the length plus 2 times the width equals 40. So that gives us the equation, which we can simplify to X plus Y equals 20. And we can isolate Y to Y equals 20 minus X. To model the area of the tray, we use the formula of the area of the rectangle, length times width. So the area is XY, and y is equals to 20 minus x. We substitute that into the equation that now gives us x times the 20 minus x. To find the maximum area, we need to take the derivative of this function, which is 20 minus 2x. We set this equal to 0 in order to find the critical point. Like solving 20 minus 2x equals to 0, we find that x equals 10. So this means the length is 10 and y is also 10. So it's not a rectangle, it's a square. So the maximum area is 100 square centimeter. We can solve for like how many cookies can we actually fit on that tray. So let's estimate that based on the amount of dough each cookies take. If we shaping the cookies into heart, each heart use about 2.64 square centimeters of dough. So we divided the tray area by that. 100 divided by 2.64, like 37 cookies. Do this with the same as stars. So we can get 53 cookies on the same tray. And this time, like we're focusing on how fast things change. The cookie dough is slowly rising and expanding. To describe this, we use an exponential growth model. The formula is y equals y0 times e to the power of kt. Here, y is the height of the cookie at time t, and y0 is the starting height, and k is the constant that depends on the oven's conditions, and t is the time in minutes. To find how fast the cookie is rising at any moment, we take the derivative of this function. So the derivative is dy by dt equals k times y0 times e to the power of kt. So this expression gives us the instantaneous rate of change. It tells us how fast the cookies is rising at a specific moment. So here's an example. Suppose the cookies start at 1 centimeter tall and the constant k is 0.2. We want to find the rate of rise after 5 minutes. Yeah, it's pretty easy. So answer is the 0.54 centimeter per minute. So this shows like how calculus help us understand the real time changing during the baking. Let's deal with like how much total transformation happens from start to finish during the baking. So as cookie bakes, the dough goes through a physical transformation. It rise, spreads, lose moisture, and eventually harden into its final shape. So this transformation doesn't happen all at once. It starts slow, become instant in the middle, and slow down again near the end. To model how fast this transformation is happened at each moment, so I created a function r of t equals 5 times sign of open parentheses pi t divided by 10. And this function describes how quickly the cookie is changing at any time. The rate start at 0 at beginning, reaches its peak at 5 minutes, and goes back to 0 at 10 minutes when the cookie is fully set. The pi t divided by 10 part adjusts the time scale so that one full cycle fits within 10 minutes. And the p-value of 5 means the fastest rate of change happens at 5 minutes. Now we want to calculate the total transformation, like not how fast, but how much the cookie has changed overall from the minute 0 to 10. So we do this by finding the definite integral of the rate function from 0 to 10 minutes. Like that means we need to find the antiderivative of that function, the left photo. And the antiderivative of this function is like on the right. We plug in the value. So we can find negative 50 divided by pi times cosine of pi and plus 50 divided by pi times cosine of 0. We can solve that, the process over there, and the answer is like 31.8. So the cookie undergoes 31.8 units of transformation during baking. Thank you for listening.
Hi, I'm Cecilia, and I'll be going over gardening with math, the bees waggle dance. What a waggle dance is how a bee moves to share information about their food source with their hive mates, and it's usually performed inside the hive on a vertical honeycomb wall. And there's two parts to this dance, as shown in the image, is like a waggle run and then a loop back, and eventually it forms a figure 8 shape. And the dance informs the bees on the distance and the direction to the food source. So how they do this is using geometry, and the angle that the waggle run from the vertical corresponds to the angle of the food source relative to the sun's position. So for example, if the food is 60 degrees to the right of the sun, then the bee will waggle 60 degrees to the right of the vertical. And the hive's vertical surface is used as a compass, where the vertical is straight towards the sun. And angles and geometry are used to translate the solar position to the directional information. The way that they communicate distance is through how long the bee waggles. So if the bee dances for a short time, then the food is nearby, and if they dance for a longer time, the food is usually farther away. And other bees in the hive watch the dance and they collect their data and they mentally average the angle and distance of where they need to go to their food. And then this is a video example of how the bees perform this dance.
And that is all for our presentations. Thank you all for attending, and a huge thank you to each one of our presenters. You guys each had very interesting presentations. So I hope all of you enjoyed listening to fun math, how some of those concepts that we learned today can be applied to real world situations and to things like games or gardening and in daily life. That's all for today. And if you guys in the audience are interested in participating in more of our webinars or even becoming part of our student board, you can feel free to visit our website, youthstemforhumanity.org, and shoot us an email to get involved. That's all for today, and there will be a webinar next month on mental health awareness. Thank you all, and hopefully I'll see you next time. Bye.